Welcome to GKE Network Policies. Welcome everyone. I'm excited to take you through one of the most critical security features in Google Kubernetes Engine, network policies. This is the kind of knowledge that separates basic Kubernetes users from security-conscious professionals. Welcome to the channel. Please consider subscribing. I produce videos covering AWS, Azure, and GCP on a daily basis. Please also hit the bell button to get notified. Welcome everyone. Today we're diving deep into one of the most critical yet often misunderstood networking concepts in Google Kubernetes Engine, SNAT and IP masquerade. This isn't just theoretical knowledge. Understanding this will save you hours of debugging production network issues. Think of this presentation as learning to install a sophisticated security system in a digital office building. You'll learn why the default Kubernetes networking is a security nightmare, and how to implement granular, firewall-like controls inside your cluster. By the end of this session, you'll understand not just the what and why, but the exact how, every command, every YAML configuration, and every security principle behind network policies. This is hands-on, practical knowledge that you can implement immediately. Let's start with a fundamental question. Would you run a company where every employee has a master key to every room? Of course not. Yet that's exactly what most Kubernetes clusters do by default. The problem: no security by default. Let me paint you a vivid picture of what's happening in your Kubernetes cluster right now. Imagine a modern corporate headquarters, a beautiful glass building, multiple floors, hundreds of employees. But here's the shocking part. Every single door is unlocked, 24/7. The intern from the mailroom can walk into the CEO's office and access confidential strategy documents. Someone from marketing can stroll into the finance department and access payroll systems. A visitor could accidentally wander into the server room and access critical infrastructure. This is exactly what happens in a default Kubernetes cluster. It's called a flat network. And while it makes development incredibly easy, with no network configuration needed, and everything just works, it's an absolute security disaster waiting to happen. Every pod can talk to every other pod. Your front-end React application can directly query your PostgreSQL database. Your logging service can access your payment processing microservice. If any single component gets compromised, maybe through a code vulnerability, the attacker can immediately pivot to every other service in your cluster. I've seen real-world incidents where a simple SQL injection in a public-facing web app led to complete database compromise because there were no internal network boundaries. This is the problem we're here to solve. Visualizing the security problem. Look at this diagram carefully. It represents the network reality of a typical Kubernetes cluster. Every line you see represents an open communication channel. Notice that there are bidirectional arrows between every single component. The front-end app, which should only handle user interface logic, has direct access to the database. This is catastrophic from a security perspective. In a properly designed architecture, the front-end should never even know the database exists. It should only communicate with the backend API. Similarly, the logging tool, which should only receive log data, can potentially query the database or interfere with application logic. Every component is a potential attack vector for every other component. This is what we call implicit trust. The system assumes that if something is running inside the cluster, it must be trustworthy. But modern security principles teach us that this assumption is fundamentally flawed. We need explicit trust. Precisely defined rules about who can talk to whom. The technical term for this problem is network overpermissiveness, and it's one of the top security risks in container environments according to organizations like NIST and the OWASP Foundation. The solution: Zero Trust Security. Network policies implement what the cybersecurity industry calls a zero trust security model. The core philosophy is simple but powerful. Trust nothing by default. Verify everything explicitly. Here is how we apply this to Kubernetes. First, we implement a default deny policy that blocks all network traffic. Think of this as our master lockdown. We are essentially putting the entire cluster under quarantine. No pod can communicate with any other pod. Then, we systematically create allow rules for only the communication patterns that are absolutely necessary for our applications to function. It is like creating specific keycards that only open the doors someone needs for their job. This approach is called micro-segmentation. Instead of having one big network where everything talks to everything, we create tiny network segments, microsegments, each with carefully controlled access points. The security principle here is least privilege access. Every component gets the minimum network permissions required to do its job, and absolutely nothing more. This dramatically reduces what security professionals call the blast radius. If one component gets compromised, the damage is contained to its immediate network neighborhood. I want you to understand that this is not just theoretical. Major companies like Netflix, Airbnb, and financial institutions use exactly these patterns to secure their production workloads. Secure architecture in action. Now look at this transformed architecture. This is what your cluster looks like after implementing network policies correctly. Notice how dramatically different this is from our previous diagram. We now have only 3 specific allowed communication paths shown in green. The front-end app can only communicate with the back-end API. It has no idea the database even exists. The back-end API can access the database and send logs to the logging tool. These are the minimum permissions required for the application to function. But critically notice what's missing. There's no direct path from front-end to database, no path from logging tool to database, and no unnecessary cross-communication between services. This is the power of network policies in action. We've implemented what security architects call defense in depth, multiple layers of security controls. Even if someone manages to compromise the front-end application, they can't directly access the database because the network policies block that communication path. Each green arrow represents a consciously designed, explicitly permitted communication pattern. These aren't accidents or defaults. They're deliberate architectural decisions that balance security with functionality. This pattern is so effective that it's required by compliance frameworks like PCI DSS for payment card processing and FISMA for government systems. How network policies work. Let's break down the technical mechanics of how network policies work. A network policy is a Kubernetes resource, just like a pod or service, that you define using YAML configuration files. Every network policy has 2 fundamental components. First, the pod selector. This is the targeting mechanism. It uses the same label selector system that you're already familiar with from deployments and services. You specify which pods this security rule applies to using labels like app, backend or role, database. Think of the pod selector as defining the rooms in our office building that this security rule governs. If you select app, backend, you're saying this rule applies to all the backend service rooms in our building. Second, we have the actual security rules, which come in 2 types, ingress and egress. Ingress rules control incoming traffic. Think of it as, who is allowed to enter these rooms? Egress rules control outgoing traffic. That's, where are the people in these rooms allowed to go? Here's what's crucial to understand. Network policies are additive. If you have multiple policies that select the same pod, all the rules from all the policies are combined. It's like having multiple security guards, each with their own set of instructions. They all apply simultaneously. The enforcement happens at the network level using technologies like eBPF or IP tables, depending on your cluster configuration. The enforcement is transparent to your applications. They don't need to be modified or even aware that network policies exist. Enabling network policies on GKE. Before you can use network policies, you need to enable this feature on your GKE cluster. This is a critical prerequisite that many people overlook. Then, they wonder why their network policy YAML files seem to be ignored. Let me walk through this command in detail. G-Cloud Container Clusters Update is the Google Cloud CLI command for modifying existing cluster settings. You will need to replace your cluster name with the actual name of your cluster, and your zone with the zone where your cluster is running. The Enable Network Policy flag does several things behind the scenes. It installs the Calico Network plugin, which is Google's chosen implementation for network policy enforcement. It also reconfigures the cluster's network infrastructure to support policy evaluation. This is a significant cluster update that will cause your nodes to be recreated one by one. Plan for this. Your existing workloads will be migrated automatically, but there might be brief service interruptions as nodes are replaced. In production, I recommend doing this during a maintenance window. After this command completes, your cluster has the security system hardware installed, but it is not enforcing any policies yet. Your existing workloads will continue to function exactly as before. Enabling network policies does not change behavior until you actually create policy resources. You can verify that network policies are enabled by running kubectl get nodes oyaml and looking for network policy annotations in the node metadata. The Foundation. Default Deny Policy. This is the most important policy you will ever create, and I want you to understand every single line of this YAML configuration. This is called the Default Deny Ingress Policy, and it is the foundation of your security architecture. Let's break this down line by line. API version networking.k8s.io/v1 tells K8s that this is a network policy resource using the v1 API version. Kind. Network policy explicitly declares the resource type. In the metadata section, name, default deny ingress gives this policy a descriptive name. You will use this name to reference, update, or delete the policy later. I recommend always using descriptive names that explain the policy's purpose. Now here is the critical part. Pod selector, with empty curly braces. This means select all pods in this namespace. Every single pod, regardless of its labels, will be subject to this policy. This is intentional. We want universal coverage. Policy types. Ingress tells K8s that this policy governs incoming traffic. Notice we are not specifying egress here. This policy only controls who can send traffic to the selected pods. The most important part is what is not in this YAML. There is no ingress section with allow rules. When you specify policy types, ingress but provide no ingress rules, K8s interprets this as deny all ingress traffic. It is like having a security policy that says check everyone's credentials but then provides no list of approved credentials. Once you apply this policy with kubectl apply-f default deny.yaml, all incoming network traffic to all pods in that namespace is immediately blocked. Your applications will stop working until you create specific allow policies. Creating specific allow rules. Now we get to the precision engineering part. Creating surgical allow rules that open only the network paths your applications actually need. Let me walk through this policy that allows front-end pods to communicate with back-end pods. The metadata name, allow front-end to back-end, is descriptive and follows a naming convention I recommend. Allow source to destination. This makes it immediately clear what traffic this policy permits. The pod selector section is crucial. Match labels. App. Backend means this policy applies to pods that have the label app. Backend. These are the pods that will receive the incoming traffic. Think of this as defining which rooms in our office building this keycard policy applies to. The ingress section defines the actual allow rules. The from clause specifies the source of allowed traffic. Pod selector. Match labels. App. Front-end means traffic is allowed from any pod that has the label app. Front-end. Here's something subtle but important. The policy is applied to the backend pods, but it allows traffic from the front-end pods. This might seem backwards at first, but think of it like a bouncer at a club. The bouncer stands at the destination, the club entrance, and decides who gets in based on their credentials. The ports section is where we get really specific. Protocol, TCP, and port, 8080 inches means we're only allowing TCP traffic on port 8080. If the front end tries to connect to the back end on port 8081, it will be blocked. If it tries to use UDP instead of TCP, it will be blocked. This is the principle of least privilege in action. We're not saying front end can talk to back end on any port using any protocol. We're saying front end can send TCP traffic to backend only on port 8080. This level of specificity makes it much harder for attackers to abuse compromised services. Understanding the enforcement flow, let me walk you through exactly what happens when a front-end pod tries to connect to a backend pod after we've implemented these network policies. Understanding this flow is crucial for troubleshooting and designing effective policies. Step 1. The front-end pod initiates a connection. Let's say it's trying to make an HTTP request to the backend pod on port 8080. At the application level, this looks like a normal HTTP request. The front end has no idea that network policies exist. Step 2. Before the network packet even reaches the backend pod, it's intercepted by the network policy enforcer. This is typically implemented using eBPF, Extended Berkeley Packet Filter, programs that run in the Linux kernel. This enforcement happens at the network layer, completely transparent to your applications. Step 3. The enforcer examines the packet and asks several questions. What's the destination of this packet? It determines that the packet is destined for a pod with the label app, backend. What network policies apply to that destination? It finds our allow front-end to backend policy. Step 4. The enforcer then validates the source. Does the source pod have the label app, front-end? If yes, it continues. Is the destination port 8080? If yes, it continues. Is the protocol TCP? If yes, the packet is allowed through. Step 5. Only after all these checks pass does the packet get forwarded to the backend pod, and the connection is established normally. Here's the crucial security feature. If any of these checks fail, the packet is silently dropped. There's no error message sent back to the front-end pod, no log entry created for the attacker to analyze. The connection simply times out, making it very difficult for attackers to map your network topology or understand your security policies. This enforcement happens for every single network packet. It's not just a one-time check when the connection is established, allowing outbound internet access. Now let's tackle a common real-world requirement. Your applications often need to communicate with services outside your cluster. Maybe your backend needs to call a third-party payment API, or fetch data from an external weather service, or send notifications through a cloud messaging platform. This requires what we call egress policies, rules that govern outbound traffic from your pods. Let me break down this egress policy in detail. The pod selector match labels role worker means this policy applies to pods labeled with role worker. I'm using a different label pattern here to show you flexibility. You might have pods that need internet access but aren't part of your main application stack. Policy types egress tells Kubernetes this policy governs outgoing traffic. Just like with ingress policies, if you specify egress policy types but don't provide any egress rules, all outbound traffic is blocked by default. The egress section defines what outbound connections are allowed. The to clause specifies the destinations. IP block CIDR quad 0/0 is CIDR notation meaning the entire internet. Any IP address anywhere. But notice the except section. This is a security best practice. We're excluding private network ranges, RFC 1918. These are RFC 1918 private address spaces. By excluding them, we're saying you can talk to the public internet, but you cannot talk to internal network resources that might exist outside the cluster. The ports section restricts the connection to TCP port 443. Standard HTTP pages S. This prevents applications from making unexpected connections on other ports. If your application needs to connect to an HTTP API on port 80, you'd need to explicitly add that port to this policy. This pattern gives your applications internet access for legitimate business needs while preventing them from scanning or accessing internal infrastructure that might be running on your corporate network. Advanced patterns and troubleshooting. Let me share some advanced network policy patterns and troubleshooting techniques that you'll need in production environments. First, namespace selectors. You can create policies that allow traffic between different namespaces using namespace selector . For example, you might allow your production namespace to access a shared monitoring namespace. The syntax uses a from field, specifying a dash followed by namespace selector, which in turn uses match labels to specify the name as monitoring. Second, DNS resolution. When you implement default deny policies, you'll often break DNS because pods can't reach the cluster's DNS service. You need an explicit egress policy allowing DNS traffic. It specifies a to field with a dash followed by namespace selector, matching the cube system namespace. It also includes a ports field with a dash, specifying protocol UDP and port 53. Third, health checks and readiness probes. Kubernetes needs to perform health checks on your pods. If you implement egress policies, you might need to allow traffic to the Kubernetes API server or specific health check endpoints. For troubleshooting, use --cube control describe network policy name to see detailed policy information. Use --cube control get pods show labels to verify that your pods have the labels your policies expect. Network policy mistakes usually involve label mismatches. Monitor your applications carefully after implementing policies. Set up alerting on connection timeouts or failed requests. These often indicate that legitimate traffic is being blocked by overly restrictive policies. Finally, remember that network policies are namespace scoped. If you have multiple namespaces, you need policies in each namespace where you want enforcement. A policy in the front-end namespace cannot control traffic in the back-end namespace. Start small in development environments, test thoroughly, and gradually roll out to production. Network policies are incredibly powerful, but they require careful planning and testing to implement correctly. Best practices and implementation strategy. Let me share the implementation strategy I use in production environments, based on years of implementing network policies across different organizations. First, always start with a comprehensive audit of your existing traffic patterns. Use tools like kubectl logs or network monitoring to understand which pods actually need to communicate with each other. Don't guess. Measure actual traffic flows before implementing policies. Second, implement policies incrementally. Start with the least critical namespaces or environments. Apply the default deny policy. Then gradually add allow rules as you identify necessary communication patterns. This approach minimizes the risk of breaking critical production services. Third, use consistent labeling strategies. Develop a label taxonomy for your organization. For example, always use app for application name, version for application version, tier for architectural tier, front-end, back-end, database. Consistent labeling makes policy writing much easier and less error-prone. Fourth, document your policies extensively. Each policy should have comments explaining its business purpose. Create network diagrams showing intended traffic flows. This documentation is crucial for debugging issues and onboarding new team members. Fifth, implement monitoring and alerting. Set up dashboards that show denied connection attempts. Monitor application error rates and latency after implementing policies. Create alerts for unexpected changes in traffic patterns. Finally, remember that network policies are just one layer of security. They should be combined with pod security standards, service mesh policies, and traditional security practices like vulnerability scanning and secret management. The goal isn't perfect security, it's risk reduction and defense in depth. Network policies dramatically reduce your attack surface and contain potential breaches, but they're not a silver bullet for all security challenges. Please hit the subscribe button if you haven't done so already. Thank you for your attendance.